Hey, how's it going everyone? Welcome to this video on chapter 13.7, which is looking at rates of change and kinematics. To start off with, we've had a look at calculus, and this enables us to analyze the behavior of a changing quantity. Now, for example, we might have a container, poorly drawn container, and we're filling it up with water. So it starts off fairly small, and over time, obviously, the container gets more filled. So we would be looking at the change in volume with respect to time. So obviously, as we have more time, there's going to be more volume of water in the container. So we need a way of talking about this change in terms of calculus, because I don't want to be having to write change in volume every time. So we say the derivative dv, because we're talking about volume, with respect to time, so it's dv dt, could be the rate of change of volume with respect to time. So rate of change or the change in volume. To be able to work out what dv dt is, we need the volume to start with. Okay, what's the volume of the container? I'm going to label that V. So V needs to be expressed as a function of one independent variable. Needs to be expressed as a function of one independent variable. Usually it's t for time. Sometimes it's h for height. Okay, what's the height of water as we increase the volume? Um, what's the volume of the container or the water as we fill up the container? So that's what we're looking at. So either one we can use. So we're just going to have a look at example 13, and we've got a cone. So I'm just going to draw that out upside down, and again we're filling it up with water or some kind of liquid. Now we don't know how much it is at any one time, but we can represent it in terms of our radius and height. To start off with, we had a radius of 2, and the height of the cone is going to be 5. Now, I don't know the height of the volume or the radius of the for the water, but I can represent the radius r and the height h at any one time. So because I've got a cone inside of cone, I can pretty much use similar triangles. So if I redraw them out as a 2D object, that's my original, which had a height of 5, length of 2, and as I increase my water volume, I've got H and R, and I want to represent the volume, I want to represent the radius in terms of H. and it's not quite easy to see. But if you remember back on similar triangles, this number here, to get to that number there, we have to multiply it by some constant. And usually we denote it by k. And same thing for 5. 5 times what gives me h. So I'm going to use that property. So 2 times k, I don't know what it is, but some constant is going to be my r, and I've also got 5 times that same constant will give me h. And just rearranging, I can say k is actually the same as h over 5. So if I put that back into that one, I'll get 2 times k, which is now h over 5, is equal to r. So just tidying up, my radius is going to be 2h over 5. Now the next part asks to find the volume in terms of h. Well, the volume of a cone is 1/3 pi r squared h. Now I know h is now 2h on 5. So I'll replace that in there. Expanding the brackets, I'll end up with 4 pi over 25, 75, and h cubed. And the final part asks to find the rate of change in which the volume changes over the height. So we've got our volume function. So essentially we're just finding dv dt. So bring the power down, divide, take 1 from the power. So we'll have 3 times 4 pi over 75 h squared. Now there's a common factor of 3 in both of those, so I get dv dt is 4 pi over 25 h squared. Now I could put that as a decimal in my calculator and I'd get 0.6 pi h. Just leave it as a fraction, usually easiest. So that's example 13. In the next video, we're going to have a look at some kinematics.